Hello everybody. Magnetic materials can be classified into three groups based on the value of the susceptibility, that is chi. If the value of chi is negative and is very less in magnitude, they are diamagnetic. If the value of susceptibility is positive but very less in magnitude, then they are paramagnetic. And if the value of susceptibility is positive and very large, then they are ferromagnetic. Here you see the inequalities give you a better picture. This is chi and the range is -1 to 0 for diamagnetic things. And similarly you have these inequalities. And note that these three inequalities are the same because you have the susceptibility and mu r, that is relative magnetic permeability, and mu, the magnetic permeability. These three are dependent, right? Given the value of one, the other two are fixed. So these three are the same. These three inequalities are the same. Multiply, no. Add one to all the inequalities in the first row. You will get the inequalities in the second row. And multiply the inequalities in the second row with mu naught. You will get the inequalities in the third row. Hope this is clear now. Just look at this table to get some idea about the values. You see these things, they have negative sign for chi, and they are very less, 10 power -6, 10 power -7, something like that. So they are diamagnetic substances, and these two, they have very high value of chi, right? So they are ferromagnetic, and these things are positive but very small, so they come under paramagnetic substances. Hope this is clear. Diamagnetic substances are those which have this tendency to move from stronger part of magnetic field to the weaker part of magnetic field. See, you have stronger part of magnetic field here, and you know that the magnetic field is weaker as you move away from the magnet, say here somewhere. So when you place a diamagnetic material, it moves from here to here in this way or this way, away from the magnet. In other terms, I can say that magnets repel a diamagnetic substance. And note one more thing. When this diamagnetic material is placed inside a current carrying solenoid, then the net magnetic field is what? It's given by this formula, right? 1 plus chi, and you have H here. Because the susceptibility value is negative here, the net magnetic field is reduced. Note that. However, it is reduced slightly because anyway the magnitude of susceptibility is very less now. Okay, the typical examples of diamagnetic materials can be bismuth, copper, lead, silicon, and nitrogen gas at standard temperature and pressure, water and salt as well. Okay, you know what are superconductors? Superconductors are those materials which, when cooled to very low temperatures, they exhibit perfect conductivity. That is, they offer zero resistance to the electricity. And interesting thing is that the superconductors also exhibit perfect diamagnetism when cooled to low temperatures. Okay, what is perfect diamagnetism? Perfect diamagnetism is exhibited when you have this susceptibility value as -1. In other words, I can say that mu r, which is nothing but 1 plus chi, is 0. This is called as perfect diamagnetism, and the phenomenon of perfect diamagnetism that is exhibited by superconductors is called Meissner effect. Meissner. Meissner effect. Okay, hope this is clear. Let's move forward. Paramagnetism. The paramagnetic substances are those which have tendency to move from a region of weaker magnetic field to stronger magnetic field. That is, if you have magnetic field lines like this, they move from here to here, weaker part to the stronger part. In other words, I can say that magnets attract a paramagnetic substance. Of course, they are weakly attracted, not too strongly. The typical examples can be aluminium, sodium, calcium, and oxygen. at a standard temperature and pressure. The paramagnetic nature of oxygen is better explained by molecular orbital theory, and this is one of the achievements of this theory, explanation of paramagnetic nature of oxygen. There, the electronic distribution is given in that way, in such a way that you have this unpaired electrons for oxygen, and hence oxygen exhibits this paramagnetic behavior. When you place a paramagnetic material or paramagnetic substance inside a current carrying solenoid, the net magnetic field here is increased because you have psi value as positive. Of course, it is slightly increased, but it is increased. For paramagnetic materials, the magnetization M decreases with increase in temperature, or I can write in mathematical form like this. When you raise the temperature, the magnetization decreases, and you know that magnetization is given by susceptibility times magnetic intensity, and I can write B naught as mu naught times H. So I have this H gets cancelled here, and I can finally write chi is equal to C mu naught by T. This is known as Curie's law, and C is the Curie's constant. Of course, I'm not writing the value because it is a material dependent property. It varies from material to material. I don't know much about this constant. What I know is that it is given by mu b square capital N G square J into J plus 1 by 3 kb. Well, you have this mu b here. Mu b is nothing but Bohr magneton. It is the least possible orbital magnetic moment that an electron can have inside an atom. It is a number. It's a constant. 9.274 to 10 power minus 24. I think we discussed about this in last chapter. Okay, this is my number. I know that. And kb is Boltzmann's constant. I know it, 1.38 into 10 power minus 23. And J is angular momentum quantum number. Everything is fine. But this N, capital N, it is the number of magnetic atoms or molecules per unit volume. This varies from material to material, hence C varies. And this G is Landé G factor. I didn't know about this. When I googled, I got something very complex which I neither understood nor I can explain. So leave it. I want you to understand this one. Just understand that the chi decreases when you increase the temperature and vice versa. There's one more thing I need to tell you. You have this equation, right? Magnetization increases with the decrease in temperature, but till what? It doesn't increase continuously to infinity. There's a limit. Actually, what happens is when you place a paramagnetic material in external magnetic field, first of all, initially there were magnetic dipoles which were randomly arranged. So when you place this in an external magnetic field, what happens is they try to arrange, or they try to position themselves in such a way that they're parallel to the external magnetic field, and hence the magnetization of the material increases. So there comes a stage where all the magnetic dipoles in the material are perfectly aligned with the external magnetic field. Well, that is the limit, right? What else can happen? So after that point, you can't expect any rise in magnetization. It's called the saturation value. Beyond that, you just take that Curie's law is invalid beyond ms. Okay. Ferromagnetic materials are those materials which move from weaker part of magnetic field to the stronger part of magnetic field. They are similar to paramagnetic materials, but the thing is they are strongly magnetized when placed in external magnetic field, and the chi value is also very greater than 1. And so when you place a ferromagnetic material in an external magnetic field, the magnetic dipoles present in this material get arranged themselves parallel to this external magnetic field very quickly and very effectively also, and hence you have very strong magnetization. When you place the paramagnetic material, inside a current carrying solenoid, you experienced a small rise in magnetic field. But when you place a ferromagnetic material inside a current carrying solenoid, uh, the increase in magnetic field will be great, maybe by 1,000 times or something like that. Ferromagnetic materials can be divided into two types: soft ferromagnetic materials and hard ferromagnetic materials. When you apply this external magnetic field, I said that the magnetic dipoles get arranged, so you have magnetization. And if that magnetization persists even after I remove this external magnetic field, then they are called as hard ferromagnetic materials. Otherwise, they are soft ferromagnetic materials. And note one thing here: as the temperature increases, the magnetization of this material also decreases. So I can say that as the temperature increases, there will be a point beyond which the magnetization will be fairly low, and I can treat them as a paramagnetic substance. Are you getting me? There's a temperature where this transition takes place from ferromagnetism to paramagnetism. This is known as Curie temperature. Beyond this temperature, the magnetization is fairly low, and so they act like paramagnetic materials. For this region, for this paramagnetic zone, the Curie's law is chi is equal to constant by T minus Tc. The reason of this transition from ferro to para can be the disintegration in the internal structure of that material. Okay, see this value, see these values of Curie temperature of various materials. They are not to remember, they are just to look, they are just to look at and get some idea about the range.